Welcome to B.Sc second year semester 3 physics students. This is Vadal Venkat Subbarao, lecturer in physics, SKVR College, Amalapuram. Today we are going to learn about interference in this first class. The learning objects for this lesson are principle of superposition of waves, coherence, temporal and spatial coherence, interference due to division of wavefront, condition for interference of light, Fresnel's biprism, interference due to division of amplitude. In this particular topic, we will discuss about change of phase and reflection, oblique incidence of a plane wave on a thin film due to reflected and transmitted light, colors in thin films, interference by a film with two non-parallel reflecting surfaces. It is also called as wedge-shaped film. Determination of diameter of wire using wedge-shaped film, Newton's rings in reflected light, Michelson interferometer, and the determination of wavelength of monochromatic lights using Newton's rings arrangement and Michelson interferometer. First, let us know about the principle of superposition of waves. When two or more waves pass through a medium simultaneously, then the resultant displacement of a particle in the medium is the algebraic sum of the displacement of the same particle due to each wave in the absence of the other waves. This means that whenever two waves meet at a point, the resultant is the algebraic sum of the two individual waves. This can be explained by this experiment. Suppose two pins are dropped in a ripple tank. The first pin produces a wave with represented by y1 and the second pin develops a wave with y2. The two waves superpose and the resultant intensity of the wave is, say, r is equal to y1 plus y2. If y1 and y2 be the displacements caused by the first and second waves respectively, then according to principle of superposition of waves, resultant displacement r is the vector sum of y1 and y2, which are the individual displacements caused by the two superposed waves. When both the sources have the same amplitude, that is y1 is equal to y2 is equal to y, then the crest of the first wave meets the crest of the second wave and the resultant displacement is maximum. And in the other case, if the crest of the first wave meets the trough of the second wave, the resultant displacement will be minimum. The maximum displacement is also called as constructive superposition of waves, and the minimum displacement is also called as destructive superposition of the waves. From this principle of superposition of waves, we can say that when both the waves meet in phase, then the resultant displacement r is given by y1 plus y2, and if the two waves meet in opposite phase, then the resultant displacement r is given by y1 minus y2. Interference is a special case of superposition of waves which originate from different sources but have same amplitude and same frequency. When two or more waves cross each other into the same medium, then the two waves superpose each other and interference will be observed in the region of superposition. Interference is the combined effect of the disturbance caused by the each individual wave at the same place and at same time. In order to get interference, we should require coherent sources. Two sources which maintain zero or constant phase relation between themselves are known as coherent sources. In daily life, it is very difficult to get the coherent sources. If we use two different sources, then the two independent sources are not coherent. Two sources derived from a single source act as coherent sources. Methods for producing coherent sources. These are the methods that are used to produce coherent sources. Young's double slit method, Fresnel's biprism method, Lloyd's single mirror method, Fresnel's double mirror method. Young's double slit method. Thomas Young is a physicist and he was the first person to produce coherent lights by making use of two slits illuminated by a source, single source. When a light is allowed to incident on a source S0, then the waves emanating from S1, S2 are secondary waves and they behave like coherent sources. They produce interference pattern which consists of dark and bright fringes. In this particular arrangement, S1 and S2 produce coherent lights and they form bands on the screen called fringes. A bright fringe appears if the light emerging from S1 and S2 interfere constructively, and a dark fringe appears if the light from the two slits combine destructively at any location on the screen. In this particular diagram, the points represented by crosses are the positions for maxima, where the crest of one wave meets the crest of the other wave, or the trough of one wave meets the trough of other wave, and the dots represent the regions of minimum intensity where the crest of one wave meets the trough of other wave and produces minimum intensity. The redistribution of intensity of light on account of the superposition of two waves is called interference. Condition for sustained interference. Sustained interference is nothing but if we get a well defined and steady interference pattern on the screen and it is easy to distinguish the bright and dark regions separately, then it is called a sustained interference pattern. The conditions for the permanent or sustained interference pattern are: the two sources should be coherent, the two sources should be very narrow, the sources should lie very close to each other to form distinct and broad fringes. This shows the condition for sustained interference. Generally, the interference pattern may be steady when the two sources should be coherent and they must emit continuous waves of same wavelength and same time period. For the well-defined interference pattern, the separation between the two sources should be small and the distance between the plane containing the two sources and the screen should be large, and the background should be maintained dark. And to get good contrast of the fringes, the amplitude of the interfering waves must be equal, and the two slits must be narrow and monochromatic. Theory of interference fringes. When two coherent lights are superposed, the redistribution of light energy in the region of superposition is called interference. At some regions, the resultant intensity will be maximum, and this is called constructive interference. These regions appear bright. At some other regions, the resultant intensity will be minimum, and this is called as destructive interference. These regions appear dark. One, consider the waves coming from two sources S1 and S2. Let the amplitude of the waves from S1 is A1 and the amplitude of the waves from S2 is A2. Consider an arbitrary point A. If the displacement produced by the source S1 at this point A is Y1 is equal to A1 sin omega t, and the displacement produced by the source S2 at this point is Y2 is equal to A2 sin omega t minus phi. The displacement produced by source S1 and S2 will be differ in a phase of phi, and the resultant displacement at the point A due to the two waves is Y is equal to Y1 plus Y2. This is equal to Y is equal to A1 sin omega t plus A2 sin omega t. After simplification, we get Y is equal to A1 plus A2 cos phi sin omega t plus A2 cos omega t into sin phi. Now, let us take a1 plus a2 cos phi equals to r cos theta and a2 sin phi equals to r sin theta. If we substitute these values, we will get y is equal to r cos theta sin omega t plus r sin theta cos omega t. Now take r as common. Using this formula, sin a plus b is equal to sin a cos b plus cos a sin b, we get that y is equal to r sin omega t plus theta. This equation represents the displacement of the resultant wave. Here r is the resultant amplitude and theta is the phase angle between the first wave and the resultant wave at the point. The resultant amplitude r is equal to square root of a1 square plus a2 square plus 2a1 a2 cos phi. When a1 equals to a2, the square of the amplitude, that is intensity, is equal to r square is equal to 2a square into 1 plus cos theta, and which can be written as r square is equal to 2a square into 2 cos square phi by 2. The resultant displacement at point P is y is equal to r sin omega t plus theta. Substituting r in this equation, y is equal to 2a cos phi by 2 sin omega t plus theta. And now let us find the resultant intensity at arbitrary point P. The resultant intensity at the point P is directly proportional to square of the amplitude, and after simplification we get IR is equal proportional to 4a square cos square phi by 2. Dividing these two, IR by I naught is equal to 4a square cos square phi by 2 by a square, and IR is equal to 4 I naught cos square phi by 2. This is the general equation to find the intensity at point P when phase difference between the waves reaching the point P is phi. Due to all these interferences, we see high amplitudes at all these points where crest of one wave meets crest of another wave, and all these points where trough of one wave meets the trough of another wave. We get a zero amplitude at all these points where crest of one wave meets trough of another wave. Interference of light. From the previous discussion, we can observe that the interference of light is the superposition of coherent lights, and at some regions the intensity will be maximum. It is called constructive interference and the region appears bright, and at some other regions the destructive interference takes place and the regions appear dark. In the interference region, alternate bright and dark fringes will be observed. Two coherent sources S1, S2 vibrating in same phase will produce constructive interference at point P whenever the path difference is integral multiple of lambda. That is, S1P minus S2P is equal to n lambda, where n is an integer. Similarly, we can obtain destructive interference at point P whenever the path difference is S1P minus S2P equals to n plus 1 by 2 into lambda, where n is an integer. These are some important formulae from the theory of interference fringes. Intensity at any point in the region of superposition is given by I is equal to a1 square plus a2 square plus 2a1 a2 cos delta. Here a1 a2 are the amplitudes of the interfering waves and delta is the phase difference between them. Condition for maximum intensity: path difference delta is equal to plus or minus n lambda for n is equal to 0, 1, 2, 3, or phase difference delta is equal to plus or minus n into 2 pi for n is equal to 0, 1, 2, 3. We all know that a phase difference of 2 pi equals to a path difference of lambda. So in this particular case, the maximum intensity is A1 plus A2 whole square, and when A1 equals to A2, maximum intensity may be written as 4A square. The condition for minimum intensity is path difference delta is equal to plus or minus 2n minus 1 lambda by 2 for n is equal to 0, 1, 2, 3. Or otherwise, in terms of phase difference, delta is equal to plus or minus 2n minus 1 pi for n is equal to 0, 1, 2, 3, that is n is an integer. In this case, the value of minimum intensity I minimum equals to A1 minus A2 whole square. When A1 equals to A2, intensity will become 0. We will get different fringes on the screen. The fringe width beta is given by lambda d by 2d. Here lambda is the wavelength of light used and d is the distance of the screen from the plane of the coherent sources. 2d is the separation between the two coherent sources. Position of nth bright fringe. The nth bright fringe will be observed at a distance plus or minus n into lambda d by 2d from the center of the pattern. And position of nth dark fringe. The nth dark fringe will be observed at a distance plus or minus 2n minus 1 lambda d by 2d from the center of the pattern. The interference pattern are observed symmetrical on either side of the central maximum. Now this is the end of interference part 1. Please send your valuable suggestions to vsrwadali@gmail.com or contact 9490885590.